Today we're going to look at problem 4.2.27, which says to estimate the parameters of the power function of table 4.12 using all three methods, and that's on page 372. So from page 373 we get table 4.12, which has the weight in pounds and height in inches of 10 male cadets on our day. So this is the respective weight and height information. And then the first thing we want to do is graph it to kind of get an idea of what that data will look like. So when we graph it in Excel, this is the graph we get. So we talked about generalized power functions in the Modeling in Real and Complex World book on page 364. And it gives us the form f of x equals a times x minus c raised to the b power plus d. And these letters a, c, and d each represent a vertical shift. Correction, A equals vertical stretch, C is the horizontal shift, and D is the vertical shift. So using these parameters, we're going to estimate a model that will try to explain this height and weight data. There are three cases that is talked about in section 4.2.1 on page 358. Case 1 talks about B being equal to N, which is a positive integer. Case 2 says that b is equal to 1 over n, again when n is a positive integer, and case 3 says that b is equal to n of some negative integer. So looking at this data, we try to figure out which case we think would work best. So it doesn't really look like an even function or an odd function, not really an integer, it's not a parabola. I would guess that it's some sort of root function. It's kind of got that square root look to it, so we would guess case 2 for this problem. So now we're going to go through the three methods to come up with our parameters. So method 1 is described on page 364, and since we're in case 2, which is the 1 over n power function, we're going to estimate the parameters for c and d. And for this case, again, since it's case 2, we're going to find where the derivative does not exist. So looking at this graph, we're going to try to estimate where the derivative does not exist. Well, it's kind of continuously moving up along here. So we'd probably go with our first point and say that here there would be if we drew a tangent line from this point, it would be straight up and down, and therefore there's no derivative. It would be the equivalent of a vertical asymptote. So we use this first point, which is the point 138 and 66, and that gives us our C and D values. So C equals 138 and D equals 66. Since that is the point where this data set, the derivative does not exist. If it was a case 1 where it's b raised to some integer, positive integer function, you'd look at where the derivative equals 0, and that would be the bottom of the parabola. But in this case, again, we're doing the case 2, and we're looking for where the derivative does not exist. So we come up with C equals 138 and D equals 66. So our next step is estimate parameters A and B. So we're going to estimate parameters A and B, and we use two data points that represent the general trend. So in this case we'll use the second and last data points. So if we look back at the graph, the second and last data points kind of give us a good idea of the general trend. If we draw a line between those two, we get a good estimate. So we're going to put those x and y values in, and we get 67 equals a times 140 minus 138 raised to the b plus 66, and 75 equals a times 200 minus 138 raised to the b plus 66. Again, 138 was our c estimate, and 66 was our d estimate, and then this 140 and 67 are our x and y values from one of the points we picked, and 275 are the other x and y values from the second point. So now we have two equations and two unknowns, and we can put this into Mathematica and solve for our A and B. So we'll use these two equations and put it into Mathematica. So we'll say n solve n solve, and then our two equations, 67 equals a times 140 minus 138 raised to the b plus 66 And our second equation is 75. Remember the double equal signs. So we've got our two equations, we end the curly brackets, and we put a comma in between our variables, and now we're trying to find A and B. And then we're trying to find the reals. We don't want imaginary numbers, so we want all the real numbers. So hit Shift Enter, and we get A equals 0.641781 and B of 0.639846. So now that we have our A and B values, we need to look at our B especially. There's a caution on page 365 in your book that talks about the value of the B parameter must be rounded to the nearest approximate value. So if you're using case 2, the power function, the computed value of B must be 1 over n, where n is equal to an integer number. So the best case for this one would be B of 1 over 2, because that gives us 0.5, because if we use 1 over 3 or 1 over 4, that takes us further away. So the best estimate we could come up with is B of 0.5. So if we round our B and let B equal 1/2, now we have to solve for our A value using that B equals 1/2. So we can again put it into Mathematica. And this time we'll use the solve command, and we just say that solve, and we only have one equation that we need to use, so we'll say 67 equals 140 minus 138, which we know is 2, and then raised to the 1/2 power, and I forgot the A, so A times 2 raised to the 1/2 plus 66, and then we're solving for our A variable. And that gives us A of 1 over square root of 2. So now we have our A equal 1 over the square root of 2, our B equals 1/2, and then we estimated our C and D parameters. So using method 1, we can get a model of f of x equals 1 over the square root of 2 times x minus 138 to the 1/2 power plus 66. So now if we want to check this model against the actual data points, we can look in Excel. That's the easiest way to do it. And we have our weight and our height in pounds and inches that we were given from table 4.12. And now we just add an extra row where it's our model, so model 1 in this case. And the easiest way is to set up our A, B, C, D parameters, and then we can lock those in and change it so it changes all the values for us instead of having to redo the equation each time. So in this case, our A was equal to 1 divided by the square root of 2, which is 0.707. Our B was equal to 1/2. Our C was 138, and our D was 66. So now we have those values locked in there, and our model 1, our formula was equal to our A value, which is this E2 cell. And then we want to lock that in, so we hit the F4, go frogs, and it puts the dollar signs in for us. And then we multiply that by our X, which is this A2 cell, so our weight in pounds, so our X. So A2, we do not lock this one in because we want it to drag down. And we subtract our C, which is 138, and we lock this in again because this always refers to this value. We raise it to the B power, which is 0.5, and again we lock this value in because it stays constant, and then plus our D value, which is 66, which is the E5 cell, and again F4, lock it in, and now we have our model value for that point. So if we go to the corner, you get that black plus sign, double click, and it'll drag down the points and fill in your data. So looking at the graph, the red is our model and the blue is the actual data. You can see that this estimate is not the best. If we are measuring error, which is the difference in the model value, our predicted Y value, and the actual value, there's quite a big gap in between these points. So you'd have to add those up, but to see that the error is pretty big in some of those points. So now we're going to look at the other methods. There are 2 more methods to look at for estimating the parameters for power functions. So now we'll go on to method 2. So method 2, again, we're going to estimate the C and D, and we'll keep the same C and D that we used before, 138 and 66. And now we're going to use the 8th data point to estimate the derivative at this point. So we're going to consider the average rate of change using the two neighboring points. And we use that 8th data point just because we're looking at trying to find somewhere that the slope's represented. This happens to be the 8th point right here. And this is a pretty average slope for the entire thing. If you draw a straight line through, it kind of covers the most of the points. So again, you pick whatever, pick the 8th one, and then we're going to look at the slope between these two and the slope between these two like we did in our average rate of change class, where we just look at the difference in the y's and the difference of x and calculate the slope and see what the average rate of change to find the derivative and what we think that tangent slope is at this point. So in this case, like I said, we're going to use the 8th point, and so we're going to look at the 8th point and the two neighboring points. So 73,185 is that 8th point, and 72,175 is the point before it. When you take the difference in the y's over the difference in x's, you get 1 over 10. And the same when you take the points on the other side, 73 to 74 and 185 to 195, again 1 over 10. So we can say that the average of the two gives us approximate derivative of f prime of x equal to 1 over 10 at that point, 185, 73. So this derivative is giving us another equation to solve for our parameters is all. So now we set up the two equations with two unknowns, and we have our first one where we just use points, 73 and 185 is our point that we picked for our 8th point, so we'll use it, and we don't know our a and our b. And then we're going to use the derivative. So that's this formula where our derivative slope f prime of x equals a times b times our x minus our c raised to the b minus 1 power. So these are our two equations, and we're going to solve those in Mathematica again. So we use the nsolve command, and we use our two equations. So 73 equals a times 185 minus 138 raised to the b power plus 66. And then our second equation, which is 1 divided by 10, equals a times b times 185 minus 138 raised to the b minus 1 power. So those are our two equations. The variables we're solving for are a and b, and we want real numbers, not imaginary numbers. So when we do that, we get a of 0.5277 and a b of, again, 0.67. So the same as the first one, we have to estimate our b to be 1 over n, which n equals an integer. So we're going to round it up. So we're going to round b and say b equals 1 over 2. And now we need to backtrack again to solve for a, using that b equals 1/2. So now we solve for a in Mathematica, and we use the solve command. And then we can just use our first equation where 73 equals a times 185 minus 138, and it's going to be raised to the 1/2 plus 66, and we're going to solve for a, and we want a number, make sure it gives us a number, not some, and we get a equals 1.021. So from that information we can come up with our model for method 2, and that model is f of x equals 1.02 times x minus 138 raised to the 1/2 plus 66. So the only change from method 1 to 2 is this a value, where now we have 1.02 as our a value. So we can look at the difference in that with our plotting, and we can just go into Excel, and since we set it up as parameters, all we have to do is click on this a cell and put 1.02, and it'll change all our values for us. And as you can see, this model looks a little better than that last one. If we calculate the error, there's only a few points that have a big gap in them as compared to the multiple points when our a value was lower. And now we're going to solve using the third method. So we have one more method to look at, and the third method we're going to just estimate b. So we're going to use a reasonable estimate based on what our graph looked like in the beginning. So on this data, the best estimate we could come up with probably is that b equals 1 over 2, because again we have to assume 1 over an integer number. So if you think this shape looks like a square root function, which it roughly does, 1 over 2, then we can say that B equals 1/2, and then we just pick 3 points and we use 3 unknowns. So we do a reasonable estimate for B equals 1/2, and then we have 3 equations and 3 unknowns. So if we pick 3 points, roughly the first, an endpoint, and a middle point in our graph, we have our 3 equations and 3 unknowns. So with these we can solve using Mathematica. So to solve this with the 3 equations, we use the solve command, and we type in solve in our 3 equations. 66 double equal sign A times 138 minus C raised to the 1/2 power plus D, and 74 equals A times 195 minus C raised to the 1/2 power plus D, and 71 equals A times 165 minus C raised to the 1/2 power plus D. So those are our 3 equations. Hopefully I didn't type anything wrong. And our 3 unknowns are A, C, and D. And we want number values. So we get A of 1.31876, C of 135.228, and a D of 63.8. So when we round that and using method 3, we get the model of f of x equals 1.32 times x minus 135.23 to the 1/2 plus 63.8. And so we can go back to our Excel and look at the model, how it compares to the actual data. And again, since it's set up, we can just change these values. So 1.32, our B of 0.5, our C was 135.23, 135.23, and our D was 63.8. So 63.8. And you can see the change, and again, it's a much better estimate than our model 2, or our model in method 1, correction. So you can look at the different models and see what you think the advantages and disadvantages are now that you know how to use the 3 methods.